design building. And I'll go a little bit specifically into mass timber and hardwood and discuss one of our projects that is on the boards currently, the National Museum of Forest Service History. And we'll leave time at the end for some Q&A. So beginning with our history and the necessity of why I think mass timber is so critical to our future, that story begins with a seedling, right? As we all know, trees grow, and because of this reason, and a unique reason as a building material, it is the only renewable material that is primarily used as a structural element. And in architecture, I think when we looked at the beginnings of history and how architecture might have began, the theorist Marc-Antoine Laugier presented his ideas about the primitive hut, right? And as we can imagine, some of the early dwellings must have been something like this, made up of wood. And we can see that in the log cabins that are throughout all over the world. And as our industry grew and we had sawmills and were able to shape and cut our logs, then we see solid heavy timber examples like this all throughout the world as well. It really certainly was the backbone of developing many of our medieval cities in Europe and the West. This happens to be Dorsten in Germany, in the heart of the Black Forest region. Across the globe, in Asia, many of the buildings were traditionally built with wood. Here's an image of the nobleman's village in South Korea. And in the United States, as the New World continued to grow and was founded, here's an image of Dodge City, Kansas, one of the frontier cities, and all of that construction is solid timber. This was the material that was available, and this was the material that was used in the development of the United States. We fast forward about 100 years to Manhattan Island, New York, and we see something quite different happening. We can see in the foreground structures about 8 to 10, 12 stories tall. Those are all you can see. They're masonry exterior wall load-bearing structures. But inside, what's holding them up are the solid heavy timber frame. But we see in the background much taller buildings, and we see really the advent of our really dense, super tall urban centers starting to happen. And that became possible given the Industrial Revolution and primarily the use of steel as a major building material. And we fast forward another 100 years. This is where all of you are very familiar with, Hong Kong, China, and you can see in the recent years with the super urban and super dense cities developments, primarily in Asian cities like Hong Kong, Shanghai, Seoul, Tokyo. Not only are the skyscrapers for just the offices and financial centers, but it really has become a typology for your everyday housing. And you can see in the foreground all of those residential towers, and the material focus changed. It was not the steel that fueled the development of those residential towers, but it's concrete. And I mention this because when we look at the whole building industry and we look at the global energy use, we account for about half the energy use, more than the transportation and the industry sector. In addition, we account for about 40% consumption of resources, 30 to 40% emission of greenhouse gas, and 30 to 40% of solid waste generation. And as we know, all of this building activity, in addition to the modernization and industrialization of our contemporary society, has led to climate change. I don't think I need to go into this in detail, but we can see all throughout the news, ever more present and more dangerous wildfires, droughts, storms. We're seeing the effects of this every day now. And it raises also issues not just of the environment, but also of the social and our community in terms of the issues of equity and the effects that it has on all of us, especially the least privileged among us. So what about mass timber for our 21st century built environment? How does mass timber and wood play into a possible solution that could help us in this current crisis that we're in? And it goes back to science and carbon in buildings. And I think all of us for the past 15, 20 years, especially in the building industry have been focused on operational carbon, right? Emissions from a building's energy consumption. And so we've looked a lot at renewable energy sources such as hydroelectric power, geothermal, solar, and wind power. But when we consider the other equation, the embodied carbon, the emissions from the manufacturing, transportation, and installation of building materials. So in other words, how much carbon has your building used up or emitted into the atmosphere even before the building was opened on day one? And I think that is something that we as an industry are beginning to recognize is just as important, if not more important, than operational carbon. And we go back to wood as a renewable material and the science behind that and the story that we all know that we learned about growing up in elementary school, that its trees are good for us and that we breathe out carbon dioxide and the trees produce oxygen. So where does all of that carbon go? It goes into the trees, and bulk of it, about 40%, goes into the growth of the trees itself as it's stored in the trunks and the branches of the wood as it grows. And couple that with sustainable forestry. Now, this view of a clear cut in Pacific Northwest may raise some alarms and may not be so sustainable, but with third-party certification and industry practices that allow for a regrowth of our forests, here's that same forest about 5 years later. And the whole issues of sustainable forestry differs from region to region in the world. There's certainly forests that you do not want to harvest and cut, but if you talk to foresters, and the industry as a whole, there is a great deal of benefit in keeping our forests healthy by sustainably harvesting our trees. And so if we understand kind of the process behind from growing a forest and sustainably managing and harvesting that to the building products of mass timber, it's a very logical and I would say a very easy process to understand. First, you have to cut down and harvest the trees. Then you're just basically simply debarking that. Then you're cutting up in terms of lumber that whole tree into smaller pieces. And in cases of mass timber and let's say cross laminated timber as an example, you're now gluing those lumber pieces back into a single solid massive panel that can really expand what wood can do in our construction. And cross-laminated timber is one of many, many materials in the mass timber category. You may have heard of nail laminated timber, dowel laminated timber, mass plywood panel, as some of the other mass timber products in the recent years, as well as glulam that I think is a material that all of us are familiar with as it's been around for over 75 years, is also in the mass timber category. So when we consider the whole embodied energy from everything from extraction, processing, transportation, construction, disposal, sequestration, we could see that in the comparison of the three major building materials, that wood is far less carbon intensive than steel and concrete, about 3 times less than steel, 5 times less than concrete. So what does that mean kind of for a typical building? This is just an image of our Adobe Hall residences, which I'll share later on in detail under construction. But that project essentially sequestered and had a positive total carbon benefit, about 4,400 metric tons of CO2. So what does that mean practically? About 937 cars off the road for a year, or energy to operate a home, 468 homes for a year. So it's a significant number, but by itself as one building, it doesn't do much. But if we start to think of how we can build all of our fabrics buildings in our cities, as our cities will expand and grow, it becomes a very, I think, sustainable and a significant strategy in dealing with the climate crisis. I'll go a little bit into the technology of mass timber because I think we're kind of at a fortunate time where there's a confluence of a advancement in digital technology that coincides for the climate crisis and the need for a solution there. Because without the advancements in technology, I don't think the use of wood as mass timber in today's contemporary buildings is possible. So if for those of you who might have been to a mass timber or a CLT plant, will understand right away that it's a very highly automated, high-tech process. It really elevates construction and production. This is a image of a CLT panel that is being laid up and put together into a gigantic 8-foot by 40-foot or 40 to 50-foot panel. And it's all automated in which these machines kind of layer and pick up the various laminates of wood. There's an automatic glue machine that goes and spreads glue upon the layers. And all of that is then fed into a giant press, where you can see here all of those laminates of wood are then glued together in a matter of it takes anywhere from about 30 to 40 minutes for that piece to be glued. And then that is then picked up and brought to a different part, a post-production part of the facility, where all of that is then shaped and cut in using CNC technology. And all of that is very important in terms of how we as designers have to design our mass timber buildings, because it is a computerized digital process in which the architect generated model is fundamentally important in terms of how these pieces will be produced. You can see a end of a cross-laminated timber panel being cut and shaped for a lap joint. And with the CNC technology, we can do pretty much any type of a modification or cut or shaping of wood that's possible. So no longer is the technology the limit in terms of what can be possible, but I would say that it's the limit of now the creativity of architects, engineers, and people involved in the building industry in terms of the possibilities of wood. Such that a incredibly complex joint like this, in which like dozens of pieces of steel and wood are joined together to make a connection, and this happens to be one of all of these points of connections, each of them of a different geometry. And as many of you might have guessed, this is the Art Gallery of Ontario, and the architect is Frank Gehry. So the ability to do incredibly complex geometries, complex buildings, as well as ability to span really long spaces. This happens to be a glulam and CLT structure at the Olympic Oval for the 2010 Vancouver Olympics. And something that I think everybody hears a lot about in terms of going tall wood buildings. This is currently the tallest wood structure, mass timber structure in the world in Norway, topping over at 24 stories. So in terms of the complexity, the size, the height, really the technology is there for us to use wood to continue to build and to expand the building of our cities and our structures. Other things that people have talked about in terms of wood, inherently wood is combustible, it does burn, is that a safe material to use? And in mass timber, this is something that the industry has known for a long time, and it's actually prescriptively written into our codes in terms of how wood behaves when it's of a big size. Essentially, it has a fire resistance that is inherent in that it chars and it protects the structural integrity of the wood structures. That, coupled with recent testing and advancements in wood fire resistance rating, is fast starting to change and update our building codes. So the IBC code of type 4 category, for example, for heavy timber construction has now expanded to 3 different categories to include up to 18 stories of building height in wood and mass timber prescriptively. And as more testing is done and more mass timber buildings are built, that height and the limitations will continue to expand and expand. One thing also that I think wood allows us to do that wasn't really possible in steel and concrete is that it allows us to research in resiliency in a way it wasn't possible. So on the right, you can see this image, and it's a little bit kind of confusing, but when you kind of carefully look at this, this is a full-size mock-up of a 6-story apartment building that's being tested for earthquake resistance in Japan. So you can see at the bottom of that image on the steel shake table frame, you can see the scale of people that are there assembled in preparation for that test. This just isn't possible in steel and concrete given the heaviness of those structures, but given one of the advantages, the lightness of wood, these type of full-size scale in terms of resiliency is something that is being tested and making our buildings safer, I would argue. So with that kind of a general background in terms of the technology behind mass timber, as well as why the importance of mass timber going forward in today's issues with climate change, I'm going to share with you two case studies of our mass timber projects. The first is called the Adobe Hall. It's a student residence at University of Arkansas. When it was completed in 2019, it was the largest cross-laminated timber building in the United States. And I'm sad but happy to also note that that is no longer the case, as the proliferation and advancement of mass timber buildings have resulted in much bigger buildings since then. The project really was about creating a new destination for student housing. Here's a kind of overview of University of Arkansas campus. In the blue rectangle is the core of campus at the center. And our project site was at the south end of the campus, really towards all of the large-scale athletic structures. And the site specifically was essentially a large empty parking lot. So in order to create a destination to get the students to come from the core of campus to the southern edge, we really had to create a place that was welcoming and a place that was desirable for the students to make that journey and to relocate. And we found our inspiration, architects design, and we find inspiration for our designs. We found it in the beautiful forests of the Ozark region, as well as the precedence of a rich history of wood structure and wood building, namely the Thorn Crown Chapel by Fay Jones, one of the masterpieces of American architecture. So we conceived of the project really as an integration of building and landscape, a weaving, if you will, of building and landscape that really created this then a serpentine shape of a building with openings and bridges and cantilevers through which various landscapes weave through. So just some finished images of the project as one approaches the project from the north. We were able to salvage a historic grove of oak trees. And as one descends the site about 20 feet in the height from the north to the south end, one goes through a landscaped environment in which entries for the buildings and the space that the landscape flows through these underside of these covered bridges and welcoming sheltered entryways really becomes a promenade and a sequence. Here's looking back at towards the north at the south end of the site, using native materials like beam rock to navigate the terrain, but also to create outdoor spaces, which then kind of flow into the inside for performance spaces and gathering spaces. And you can see on the ground floor the exposure of the mass timber structure, the glue lamb, columns, and beams, the underside of CLT floor decks are all in view of all of the visitors and the people that use the structure. In contrast to a very open ground floor and the images that I shared with you, really the emphasis of this project as a housing project was to create a very super efficient set of plans that laid out the maximum number of housing units. And you can see here, given the serpentine shapes, you can see how packed it is with the student dorm rooms, but we've allowed for, in red with the circulations, common gathering spaces at the knuckles for social activities among the students, as well as at the end of corridors where we allowed for the daylight to come in, as well as to provide study spaces at the end of corridors. So as I said before, in looking at mass timber, the efficiency and really I think the strategy of how to design at the very beginning, looking at the very panel and how the understanding of these CLT panels are integral, it became a kind of I think a strategy and exploration for this project. So as I mentioned, the cross-laminated timber panels are produced in really big sizes, and when we looked at the panel sizes, we kind of came to an 8 by 40 panel size, given that most of the suppliers could produce this panel. And that was important because this was a state project and we couldn't go to a single source supplier, but we had to make it possible for multiple suppliers to bid and to increase efficiency, increase the cost favorability to the client. We set the panel size so that we could have as much competition among the suppliers. And so based on that A540 panel, we worked carefully in terms of the double-loaded corridor and the size of the dorm rooms to create a building that was about 60 feet wide with a column grid of 24 feet, allowing for 3 bays of the 8x40 panels in the staggered position. And once that 8x40 panel is produced, then every other one could be cut in half and to then fill in the remaining spaces. So with that basic idea, that we studied each segment of the mass timber structure of each of the serpentine wings, and what we ended up was a very simple structure in which we had a glulam frame with columns and beams, and then with this array of cross-laminated timber for the floor and the roof. And in this case, we used a site cast concrete for the egress cores, given the regulations in this area about fire egress. So with that basic understanding, it was a back and forth discussion and collaboration between the architect and the structural engineer in laying out a very highly efficient and modular set of structural grid. And then that would allow us then at the corners where the angles were, where the dorms were not, and which were the specific spaces, then to be able to accommodate and to make the flexible changes in the angles of the grid. And that's translated then into this is a image from the construction document set, and you can see here that same 8 by 40 foot being the basis of this highly modular layout of the dorm rooms and the structure. But when that came to construction, and once we settled on a supplier and started the shop drawing process, something changed in that if you look carefully here, these panels are much more narrower, and they're essentially 4-foot wide panels instead of 8-foot wide panels. And this is something to note, is that given mass timber and the fact that many of the suppliers still are doing things quite differently from each other, they use different species of wood. The way they lay up the glue and the sizes of the laminates that they use, they vary slightly from manufacturer to manufacturer. So in this case, the supplier that was selected, which was out of Austria, produced as a commodity product these panels that were 4 feet wide instead of 8 foot wide. And that allowed the client to get quite a favorable price in the CLT panels. And so this meant that we would have to have double the amount of joints, double the amount of lifting these panels up for installation. And that was something that was important to work out with the supplier before finalizing the agreement, so that all of those installation and construction aspects could be accounted for, and not just the price of the panels themselves. This is just a quick fly-through of the overall building, and you could get a sense before the cladding of the incredible modularity and the simplicity of the upper volumes, the upper levels of the structure, which houses student dorm rooms. And then in contrast, the openness of the ground floor, and as I'll get into later on, the combination of wood working in conjunction with concrete as well as steel to create the experience that we were seeking in this project, but one that could also then use each of those material in a smart way for their advantages. So here's an image of the building under construction. You can see the upper floors where the student dorms rooms will be, the mass timber structure of glulam columns and beams and CLT floors. And on in contrast, the openness of the ground floor. And here we're using steel beams to create those openings, those transfer beams, those cantilevers, because steel, in terms of being able to do those elements is much more efficient than wood. But wood, given the fact that in terms of its strength to weight ratio is much more stronger than steel or concrete, possesses those advantages and allows for us to then make these highly regular, highly modular areas of a project much more efficiently, much more cost effectively. As we all know, once we deal with the structure, then we have to deal with all of the infrastructure, the systems, the MEP, and the fire protection. This is, again, using that 3D digital model that we use to create the structure and using it also for the coordination purposes. And I emphasize this because in the design of mass timber structures, given that most of the elements are prefabricated in the factory and brought to the site, and rather than being construction happening on site, it's really the assembly on site. That means a lot more coordination has to happen between the architect, the supplier, and the contractor before construction happens. And that pre-planning is incredibly important, and a digital model is necessary, especially in our case here where it was a housing project. We had many, I think it was over 4,000 penetrations. All of this is an image from the shop drawings from the supplier that coordinates all of those penetrations in the CLT structure. And you can see that when it was arrived on the site, it came with all of these openings pre-drilled, prefabricated in the factory, so that on the site it was just a really easy lifting of these pre-assembled elements of plumbing and other infrastructure in place. And we coordinated carefully where all of the ducts, the pipes, the conduits would be, namely along the interior of the space along the corridor. That then allowed us to really open up the perimeter, the lounge spaces, the student dorm room, the very fabric of the building itself, so that we could expose all of that beautiful cross-laminated timber with structure, but also to keep all of that surface free from light fixtures, sprinkler heads, fire alarms. Where might those be? Because those are still necessary. And they're just beyond the image here from the point where the photograph was taken, where we used the wall-mounted light fixtures, sprinkler heads, fire alarms, in a way that was well coordinated with our consultants to really leave that ceiling plane uncluttered. And that point where these overhanging upper volumes with the student rooms then joins together all of the public spaces on the ground floor, such as the maker spaces, the main community spaces, the community kitchen, and a variety of classrooms for this live-learn community became, I think, another way of exploring and looking at how wood with conjunction with other materials like steel and concrete could be used in a seamless way. So that area that I just showed you, here's a section of that with wood structure that's kind of shown in red for the upper volumes, and then the lower structure, and you can see in blue the structure for the steel that cantilevers and transfers those loads and allows those openings to happen. And in the background then to use local wood for finish cladding as well. So here we use the local Arkansas cypress, a hardwood, to shape and to clad many of the public spaces on the ground floor. And that covers up kind of this intricate connection between steel structure, which is shown in blue, and timber structure, which is shown then in red, in which that had to be absolutely coordinated with the concrete core that's shown in black there. And you can see kind of an image of that in which the three different materials come together to create this cantilevered moment with a mass timber structure above, the steel cantilever frame, allowing that to happen, then in conjunction with site cast concrete. And as I end this case study, just to focus on the project's main central space, this is called the cabin. This is the main community room. And this was the largest spanning space of the project. And so we used a simple truss geometry for material efficiency. It also had an elevated roof with a roof garden on top, so that we had to accommodate between the height and the level of the rooftop as well as the level of the overall ceiling, and came up with this queen post truss geometry to efficiently accommodate those two levels. Here's the On the left, the wood structure, and then on the right, how that integrates with the rest of the architecture. A quick exploded axonometric of the various components from the top, the landscape accessible green roof, the CLT panels for the roof slabs, then the cypress slats for to conceal the mechanical zone in between, which then is supported by the glulam and steel structure that then sits on a concrete-based slab. So you can see an image of that main space there that really then takes a full advantage of, I think, the beauty and the calming and the restorative effects of mass timber and wood. And looking at the detail, then we were inspired by Faye Jones and the Thorn Crown Chapel of this masterpiece in light frame wood construction, and this really how the joint dissolves in this case here with this kind of almost impossible void at the joint where all of the wood members come through. And that started out as an inspiration for us in terms of how to make this joint between one of the critical key joints in this truss. And we started out on the left with a simple sketch about creating that same type of a hole, a void. And in the middle, when we started to do the engineering and with our structural engineer, given the amount of forces that were required in this mass timber structure, especially with the roof garden on top, the timber members could remain at about 6 inches, but to create that void, that steel connector would have to be much bigger. And to create that void, it would then have to have all of these tension rods and their anchoring points be exposed to have enough thread to allow that for connection. So after exploring this, we kind of came to a point that what we were pursuing was, in fact, a kind of a misalignment in terms of concept of the project and the aspirations. And we said this is not a light frame structure in which that void is possible and warranted, but it's a mass timber structure in which we should embrace that mass, so that what began as a void then became a solid connector, preserving the original intent of the proportion between the steel connector and the wood members. And again, then using really the ease of digital fabrication, use of CNC machines to cut the wood, that joint became very simple, in which all of that cutting then allowed for the integration of the steel joint, as well as all of the connection tab that was necessary to be hidden between the members. And you can see the cut of the wood with the CNC machines that allows for all of that connection to happen, and a detail of that just before the steel members get painted in the field, and an overall view. And as much as this was about the exploration of the digital technologies that made this building possible, at the end of the day, it's about the students and the life on campus and the live-learn community that we were able to create, and really how wood can then benefit the everyday lives and the well-being of its occupants. Moving on to our second case study, this is the Oliver Design Building at UMass Amherst. This was completed in 2017. It was actually prior to our Adobe Hall, and another different typology. This is a higher education classroom building, and the setting for this was in a rural western Massachusetts, and this is an image of the region, and you can see kind of in the back, in the middle, some taller buildings, and that's the campus. That's the UMass Amherst campus, which is the flagship University of Massachusetts system. And we were really inspired by the regional context, the patterns of the agrarian fields, the sustainable culture there, as well as historic, beautiful, original heavy timber structures such as these tobacco barns. The project here was to bring together 3 departments that study the built environment, namely architecture and design in blue, building construction technology in yellow in the map here, and landscape architecture and regional planning. And they were all in 3 separate buildings, and the university had the foresight to bring together all of these disciplines across different colleges into one building. The site that was selected was shown here in the red dot. And looking at that site, it was highly important given that it was really at the knuckle between two different areas of the campus. The main center and shown in blue and the main central campus space were these large monumental 1960s and 70s concrete structures that set the grid for the future development of the campus. You could see the orientation of the rest of the campus. But on the other side of our building was the original campus, which was over 120 years old, shown here in kind of a salmon color, a much different scale of buildings. And you can see here the contrast between the west-facing side of our site, the large monumental concrete structures, and on the east, the original campus of the Stockbridge Way, smaller wood structures, two-story brick structures. So our concept then was really the coming together of program on site. We used a courtyard typology to bring together the three departments and to have that necessary common center. But to avoid the inherently insular characteristics of a courtyard building and looking at the site and taking clues from the site, we opened up the courtyard in plan, and we also then lifted up one end of it in section to respond to the different scales surrounding the building. And you can see in this section perspective, this lifted courtyard that allows the ground floor to be transparent and accessible from the rest of the university. Then the central space, then we decided to divide that into a two-story central commons where all of the departments could gather, and above it, an open roof garden for the landscape architecture department to showcase their green roof technologies. A view of the central common space where everything in the building can be seen, everything from studios, offices, seminar rooms, classrooms, and even the industrial spaces, the Mega labs, the wood research lab, the testing labs, you can see on the ground floor just across those interior glazing partitions. And then the roof garden that is on top, that is then supported by the mass timber structure. Looking at the overall kind of open courtyard plan and the exploded axon that shows the structure. In this case here, in addition to the similar glue lam post and beam structure with cross laminated timber floors, we were able to actually look at all of the shear cores in cross laminated timber. There was no need for concrete here other than the foundations, and that was also a big development and demonstration of capability of cross-laminated timber. You can see here a photograph of the building under construction. The framing is about 85% or so complete at this point. A closer look at a segment of that. And looking at a typical column and beam joint, one might see in older solid heavy timber structures a joint like this, in which you have an exposed steel connector that brings together the column and connects it with the beams. Well, where is that connection happening here, and how is this indicative of some of the digital technology that I've been talking about? Well, the connection is there. It's just that it's hidden, and there's some of these advantages here in that, as I've mentioned earlier, when exposed to fire, mass timber will char, and the inner area will be protected and maintain the structural integrity. And it keeps this critical steel joint from being compromised in a fire by being protected by wood. It's kind of ironic, but given how wood behaves in the fire with charring versus how steel behaves in a fire when left exposed without fireproofing, it will melt and lose structural integrity. This becomes a very favorable condition that's advantageous and inherently fire resistant. And this is again possible because of the CNC machining and the ability to cut and shape the wood to receive these connectors. And another advantage is that instead of welding or bolting together complicated steel connections, these are all then pre-installed in the shop, so that when the members are brought in, the beam is then lifted and just slid into place, so that it's a very super fast installation process. Looking at one end of the building where we did not have a core and we had to do bracing for the shear, you can see that installation process as well here. And again, how the pre-assembly of all these components results in the field, basically a simple pin joint that goes through 7 different layers of wood and steel, and the accuracy and the precision that's needed to make sure that those layers between the steel and wood can be possible given all of these tiny high strength pins that lock those members into place. And overall, as the construction was happening, it was really indicative of the speed of construction and really the small amount of workers necessary that is typical in a mass timber building. You need a crane operator, a crew of a person organizing and coordinating, and a small crew of usually typically about 5 to 7 people in terms of receiving these panels, screwing them into place, and doing the overall frame installation. At the University of Arkansas, in this case here, as typical with mass timber structures on floors, because of the lightness of wood, one of the disadvantages is that it's issues of acoustics and vibration, and you need mass to deal with these very important aspects of public buildings. And so you'll see that typically a concrete topping or a gypcrete topping on top. In this case, what we used was a composite technology, which was researched in part by the professors at the university, in which a perforated metal connector was installed, and you can see those fins sticking out of the CLT panels, and that allowed then when the concrete was poured on top with a layer of acoustic insulation in between, for the concrete and the wood and the CLT to be mechanically fastened together so that the wood was not taking on the dead load of the concrete, but that it would work structurally with the concrete taking the compression and the wood taking the tension, so that allowed for a longer span, a more durable floor system, which could then take on the 100 pounds per square foot instead of the 60 or 40 pounds per square foot that was typical in these classroom buildings, and allow for greater flexibility and use of assembly spaces within the building in a flexible manner. Mentioned earlier a little bit about the cross-laminated timber for the shear walls. Here is one of the elevator cores that are being constructed of CLT panels. And again, in terms of how much time this would take in a site placed concrete or a fully grouted CMU wall, which would take weeks for that to happen. Again, this was installed in a matter of 2-3 days over a weekend, again highlighting the incredible speed of mass timber construction. We used it also on the various egress stairways as well. And in this case, we were able to leave exposed the cross-laminated timber on the inside of the exterior of these egress stairways. Looking closely at the center then, how the central space really was the largest span. Again, an opportunity really for an expressive way to use mass timber, glue lam and cross-laminated timber to shape that space in a way that it would be able to take on this load of a fully intensive roof garden on top. We explored with our structural engineer the idea of the geometry of the truss, which could be repetitive and could work easily within this trapezoidal space. And we got going early on in terms of, again, a digital modeling. This is the Rhinoceros model tool, which allows for complex geometries to be worked out. And this was important not only for communicating with the supplier and the subsequent fabrication of the various components of mass timber, but also then allowed us to produce our contract required construction documents. So the model then became the basis for producing all of the drawings, such as the reflected ceiling plan, the profile of the truss, and all of its details. And you can see how that then led to a very easy coordination and a conversation with the supplier in terms of fabrication. As I focus a little bit on that connector, this is, I think, I show these series of parallel sketches between the structural engineer and the architect, because that integration between the engineer and the architect and that close collaborative working relationship is absolutely critical in mass timber buildings, because the structure more often than not tends to be exposed and expressed. So going back and forth between early ideas about a very simple plate connection at the joint where all of the truss members come in, and realizing that that didn't, again, have the required mass to take on the forces, and then going to another strategy, a sphere, that would allow for the flexibility of the geometries, but one in which we didn't like the bulkiness or the aesthetic of that solution, which then led us back to the drawing board in this often iterative process in which we came up with a cylinder as a shape then that would accommodate and have enough of the mass to accommodate the forces, but slightly shaped, and again with the plates to make that connector happen for the final version of that connection. Here's an image of the center connector after it's been fabricated. Then we looked carefully in terms of also a balance of the cost of such a connection, making sure to use off-the-shelf products as these tension rod ends that were commonly available to us to reduce cost. And then where we had to cast a specific connector, making sure that we could do that with a single cast that would work for all 57 members of these joints to save on that production cost as well. A few images of the central space under construction. We thought a lot about how to install this, everything from having it pre-assembled and brought to the site, which was a logistical issue given the tight roads leading to the job site, to everything from looking at it pre-assembled on the site and then lifted up in place. And as construction goes, it doesn't often go according to the way you've planned. And one of the critical members was there was a delay in fabrication. So rather than delaying the whole project, the course that was taken was to shore up this central space so the work above it could happen parallel and until the members arrived, in which case then piece by piece, this was then the geometry was then put into place in the location elevated above, and you can see the workers starting to do that. And this was that interesting moment where we were called as architects and engineers to the site. This was the moment where all of the geometries of the truss was installed and connected. And the day that the shoring that you see in this photo would be let go. And here it is after that shoring has been taken out, and everybody breathed a sigh of relief in the fact that this truss would do what we designed and engineered it for it to do. And again, a view of the central space. And above that, a rich roof garden that allows for a variety of functions, from outdoor classrooms to evening events, and really becomes a place where the landscape architects can really look at and study roof garden technologies. Here was the image of the building just about a few months after as the landscape is yet to grow. A year later, the landscape is thriving and in need of maintenance. And this is what the landscape students do as part of their course curriculum. They go and learn how to take care of the various vegetation on the rooftop. And this is New England. Again, we deal with big snowstorms, and even given the nature of the four-sided enclosure of this courtyard and the issues of snowdrift, this was a photograph that was taken by one of the user clients and sent to me. They were worried that, have you guys designed this wood structure to allow for all of the snow load? And rest assured we did, and this was a great way to communicate the durability and the strength of wood as a structure that could then take on all of the things that we're used to seeing from steel and concrete. And again, the final shot of this project. We design buildings and we often anticipate how our users might use these spaces. For example, this space here for gatherings, for quiet study, for events. But sometimes how users perceive our spaces are quite surprising and a pleasant surprise. And I show this image because about a year or so after the building was completed, the city of Amherst took a poll, and I don't know why they took this poll, but this courtyard rooftop garden was voted the most romantic place in all of Amherst. And perhaps it's not surprising because I know college students date, and so I think this image is a very indicative picture of that. So as I kind of end the presentation, I'd like to talk a bit about mass timber and hardwood. If you look at the vast majority of cross-laminated timber buildings that have been built in the world today, and there's thousands and thousands of them, so this is people think this is new, but it's not new. It's been happening in Europe for about the past 25 years in terms of CLT technology and use, and in Canada 15 years or so, and in the United States 10 years, and you see it in all places around the world, CLT structures. But a vast majority of is made from softwoods. You see the most common varieties here: spruce pine fir variety, Douglas fir, which is prominent in the Pacific Northwest and known for its beautiful rosy color. And in the southeastern United States, the southern yellow pine, which is the largest wood basket in the United States. But why is that? Why is it so? Why is that it's been softwood that has been the prevalent material? And I think it comes down to economics, as most things do. First, you look at the cost of softwood versus hardwood. Softwoods tends to be much less expensive. And because of that expense, traditionally hardwood has been used for finishes and not lumber. And if we go back to the earlier in terms of how the CLT panels are produced, the main ingredient is lumber. So most of the sawmills are softwood lumber mills, and the sawmills that use hardwood are used for not for dimensional lumber, but for finished lumber. So they're calibrated slightly differently. So all of that kind of adds to in terms of why we've seen softwoods. But that's also fast changing. There's inherently nothing inherent about hardwood in terms of its acceptance or approval or use in cross laminated timber and other mass timber products. And I would argue that there are a lot of advantages instead. And one of the species that's most prevalently being studied is yellow poplar, or also known as tulip wood. It is the most abundant hardwood species in the eastern United States, and its use of especially a low-grade appearance wood, which is cost competitive with softwoods, and it's being used mainly in a lot of the pallet-grade lumber. Testing has been done by various researchers, and all of this information with credit in terms of regarding hardwood comes from Dr. Henry Quesada, who John and I met about 3 years ago through our mutual connections. He's a professor currently of forestry and natural resources in Purdue University, as one of the leading researchers in hardwood application in mass timber. And testing has been done in which that 95% of that low-grade, cost-competitive yellow poplar is qualified for structural CLT use. And recent APA results have shown outstanding, structurally better qualities and testing results than southern yellow pine. And additional hardwood species that are in research and favorable in terms of use for mass timber would be soft maple, red or silver maple, sweet gum, basswood, sycamore, to name a few. John mentioned earlier on that the Multiply project was a installation that happened, I think, back in 2018 that showcased the use of hardwood. Here you can see an image of that. Also, many structures since then. On the upper right is a permanent hardwood CLT building in UK. And here in the United States as well, a lot of installations and structural hardwood CLT projects that are starting to be built. A conversation plinth in Columbus, Indiana that used Indiana hardwood for its CLT, a mixed variety. As well as most recently a train observatory in the Forest Preserve in Radford, Virginia, a combination of projects done by Virginia Tech professors in their research, which was the first structurally accepted hardwood that went through all of the testing that the CLT needs in terms of the the North American production of meeting the PRG 320 using yellow poplar and having that accepted as well. So I end with our last project, the Conservation Legacy Center for the National Museum of Forest Service History in Missoula, Montana. This is a museum that celebrates the U.S. Forest Service long conservation efforts in preserving our national forests and grasslands. And the project was really inspired by the Forest Service and the forests themselves. The site in conjunction was a beautiful site with the forested mountains in the background. And that became really the inspiration for the early concept sketches of creating the museum that really evoked the sense of the trees and the forest and the folded mountain roofscape. And that main area then became a place for the building to be an exhibit in itself, really utilizing the rich variety of tree species, most of them hardwoods in terms of the mass timber structure to create these tree-shaped columns, everything from red oak to sugar maple to white ash to cypress. So this is a mass timber structure that will incorporate both hardwood as well as softwood. You can see the kind of the rich variety of the textures and the color and the grain that will create this the main space with the warmth of the wood, but also the richness of all of these different species. The idea was really then to create this experience of being in a forest. I think a kind of a soaring space that's often embodied by Gothic cathedrals. Here's one in Bath in English High Gothic. And how we could aspire to do this in wood, looking at the reflective ceiling plan perspective of our structure. Looking at the cross-section, the building really then becomes a way to observe not just the building itself, but the various processes behind the exhibits, everything from repository processing to receiving areas, and also the incredibly rich site that has view holes from the various parts of the buildings to engage the site as well. And we're currently in schematic design and looking at the development of the mass timber structure using a variety of hardwood species, especially for the tree-shaped columns and some elements of the folded cross-laminated timber roof. Going through various structural analysis in really balancing the structural efficiency as well as the aesthetics and the overall feel of this forested canopy. And just a quick video of that project. Excuse me for a second. You can see the main approach to the building from the south. A colonnade of these tree-shaped columns provides a shelter from the southern sun in the summer that allows then for the daylight to come in the winter, and a rendering of how we envision that space to be in connection with the exhibit areas, but also that main lobby being an exhibit in itself. A generous south-facing hallway that then provides access to all of the museum's program elements. Here's a look into the gift shop, which is critical to museums as well for its fundraising purposes, flexible classrooms and event spaces for educational purposes, and really this sheltered colony along the front, really to then enjoy the beautiful views of the mountains beyond. So this is currently in design, slated to be finished in design this year and to continue into construction next year. So in conclusion, I'd like to just end by saying that, I had this thought when this is an image that I took when I was on the construction site at our University of Arkansas student housing project. And these three-story columns were reminiscent of where the wood came from, our forest, right? You can't escape this comparison here. And all throughout history, the trees have served us well. From these incredible structures like these hanging monastery in China, where the tree trunks were used for the support structure of this, to the amazing craft of some of the older wood structures. Here's Old Faithful Inn, to those of you who may have been to Yellowstone National Park. An incredible structure with essentially just using the logs and even the curved branches found in nature to create these connections between the columns and the beams, and how we're continuing to use the wood and using it in a way that allows us to have greater possibilities in terms of size, scale, complexity. But at the end of the day, it's that same material, same renewable material that which we used to build with I would say, prior to the Industrial Revolution and the advent in which our society started to emit incredible amounts of carbon. And could we then go back to that time where this renewable, sustainable material was used primarily to build our structures, but in a way combined with the modern technology that's necessary to create the buildings we need today? A detail of that staircase, which was basically a half-cut log to make the stair riser and treads, compared with the CLT stair and glulam blocks that happen at our design building for the main stair. And often I go to national parks with my family. This was a few years ago when the kids were younger. We visited the Sequoia National Park. This is the General Sherman. I think this is the largest tree in the world in terms of volume. And it reminded me again, it's, there is this incredible, I think, affinity and the connection between us as human beings and trees. We both aspire, we aspire and we look to the sun for the height, and we build our structures that way. But I think there's something more. And I leave with this final images when I visited the Korean Furniture Museum in Seoul, South Korea. This was where I was born before I came to the States. And this was historically a royal residence. And as I was entering the building, and as I crossed the threshold of that doorway, this was over 100-year-old pine wood door that was still seeping the sap after all these years. And it still reminded us where it came from. And this is, I think, something very important for us to not lose sight of as architects and engineers and designers, is that given all of the technological advancements that allow us to build differently and in wood, we can't forget the very essence of wood itself, how it's connected to us and how it makes us feel and how it creates spaces that I think promote human well-being given its biophilia. So with that, thank you for listening to my presentation, and I'll hand it over back to Evelyn.
Great. Thank you so much, Tom, for your presentation. It was really interesting to see not only the kind of background of mass timber, but also seeing the different case studies that you presented, the design process, and also ultimately how users engage with the building in different ways. I want to start off with a question. I'm curious, when you were presenting the 3 case studies, because they were all, well, the first 2, they're educational buildings. I wanted to know if the intent of using mass timber for the structure came from the institution, or also in your design process, whether it was a kind of starting off point, or you developed the massing of the building and then the desire for introducing timber and the kind of sense of materiality came later. So maybe could you talk a bit more about when the desire to use CLT came in?
Sure. They were slightly different for each of those projects, and first, they're both higher education projects, mainly because that's kind of the primary sector of our office in which we do our projects. We do most of our projects for higher education and universities. But having said that, the Alver Design Building was essentially, when we got the project, was advertised as a steel building because that's the material that's most common in the Boston area, in Northeast United States. And there was just this one sentence about a professor who wanted the aspiration for mass timber. And we studied this early on, but we actually went through almost to the end of design development with the building as a steel structure until a kind of a sustainability bill was passed in the legislature, which allowed for additional funding to have the building be built in mass timber. And so after having gone through design development, we switched from steel to wood, which, as those architects, or those of us that are architects in the room understand, it's not the best time to switch structure. But a pat on our own back here. We knew that there might be this slight possibility, so we made sure as we were designing this in steel that very fundamental things like column grid spacing, column sizes, beam sizes, those things could be done either in steel or wood, so that if a change was to happen, then we could keep the design, we could develop the kind of the central zipper truss area, but that we wouldn't have to stop for 6 months and redesign the building, but that we would take, and so instead of that, it took us about a month to then translate the drawings from the steel structure to wood structure and to relatively carry on with the projects without losing much time. The Arkansas project, in contrast, started out where the client wanted a mass timber building. So the list of firms that interviewed for that project were firms that had prior experience in mass timber, and we were fortunate, just having finished the over design building, that we had some like last minute built photographs to present. And you can see there in my explanation, because cost is, again, everything, money, it comes down to money, as the famous saying goes, and we had to make sure that we could build that project within the cost parameters of a typical steel building at the University of Arkansas. And having done the over design building, we knew that given the modularity of wood structures and mass and CLT and how they're produced from panels, and the less you have to cut and the more you could use those overall billet sizes to its maximum potential, there would be tremendous cost savings. So that's why that 8-foot by 40-foot panel size, which most of the suppliers could produce, became the module to then shape the overall dorm room, which then became the module to shape the hallway and the section of the building to the segment, and then finally arranging that in the serpentine shape. And again, I mentioned cost a little bit here because I'm sure maybe there's people have questions about cost comparisons. And given that mass timber over the past 15 years or so has been a new construction type that's been adopted and introduced to the building industry, it's historically carried a premium when compared to steel or concrete, but that premium is fast narrowing in terms of that gap. And the question is mass timber more expensive than steel or concrete? The answer is it depends on the project. There are many cases where mass timber is less expensive, many cases where mass timber is cost competitive with steel or concrete, and in cases where mass timber is more expensive. So it really depends on various factors of the project, I would say.
Right. And I guess this is something that you've also touched a bit upon in your presentation, is that it's very much, because it's a relatively kind of, with the innovation of different wood joints, that it's a relatively new technology, and that it's a very collaborative, has to be a very collaborative process with the structural engineer, with suppliers, in terms of getting those fixings right. And then you mentioned on the, I think the Adohi Hall project, that there were slight modifications when it came to after the supplier was selected. I wanted to know if there's a lot of kind of redesign that's involved once the supplier is selected, and how that affects, if that has had a significant impact on your kind of design, and whether certain, let's say, key details that you had envisioned earlier on in the design process, how that has changed once you reach construction stage.
Yeah, really, really great questions. The first part of the question and the comment that you made about the technology allowing us to make connections that really weren't possible before, I would qualify that, because if you look at old wood structures, the beautiful temples in Asia, for instance, you have master craftsmen making incredibly complicated joints like mortise and tenon joints, and you can see this even in the United States in the arts and crafts movement. They didn't have computers back then, they didn't have CNC machines, but it required a master craftsman that devoted his life, essentially who was an apprentice to his father, to his grandfather, to learn that skill. And what the current technology does is it makes that skill ubiquitous and available for all projects, not just the very few special projects, but you're down to your everyday housing and office buildings because of what the CNC machine can do. So I think it's a lot of it is about the speed and the efficiency and the economy of being able to make these incredible connections that that frankly, if you look carefully enough, we've been doing in terms of the rich history of wood architecture. Going to the second question about the various suppliers, this again is something I think if you look at mass timber 25, 30 years down the road, you'll have quite a good set of standards, I think, across all of the suppliers. But right now, there's, for a variety of reasons, each supplier makes their CLT panels, glue lamps slightly different. First is species of wood. Um, Trees are different in different areas of the world, and depending on each species, they have different characteristics. So, for instance, at Adobe Hall, we designed this based on actually a Douglas fir as a species, as the main species type. Because the supplier that we ended up with was Binderholz out of Austria, and they made their CLT based on European spruce pine fir, what that meant was that for the same structural criteria, the Douglas fir was stronger than the European spruce pine fir, so that the floor depth and the beam depth in Douglas fir was slightly less than in European spruce pine fir. So there was most of all, it didn't make a huge difference, but there were a few cases where we had tight spacing between the bottom of the beam and where the ducts, mechanical ducts, would go underneath, and we had to calibrate and make some adjustments there. So the way to avoid, and people who've done mass timber buildings know this, is that given this inherent slight differences between the suppliers, it's best to have a supplier on board before the construction documents are done. As to when that happens, I think depends on project to project. On private projects where you can talk with and have a supplier on board early on, it's often better because there's less redesign and you can work together with the supplier. The risk to that is that you take the competitive bidding out of the picture, right? Because you're dealing with one supplier. So the process that we took, and partly because the projects that we work on are primarily public projects where you can't have a proprietary supplier without going through a competitive bid process, is that we will design the project up to about let's say beginning of construction documents to anywhere about 50% construction documents, where the design is complete. We have a sense of what all of the pieces of mass timber will be, a general sense of what the construction connection concept might be, so that we can bid this out to several suppliers and have a competitive bid without a high risk of change orders. And then once we select that supplier, then for the kind of the second half of construction documents, we're working in parallel with that supplier based on their species, based on their preferred connection types, so that those details can be worked out so that the shop drawing production process can happen before construction starts. So that again, all of that coordination can happen with the systems, the MEP fire protection systems, and that the work that's done then allows them to speed up the construction and save time in the construction part of the project.
I actually also have a question about the species. When you're doing, say, interior fit out for furnishing using the wood, a lot of the time the decision on the species was based on aesthetics, on the color, the appearance of the wood. But when it comes to mass timber, do you have that kind of consideration as well, or is more driven by the availability from the supplier?
Yeah, I think it's a combination of both. Because the recent focus really has been on making our mass timber buildings competitive with steel and concrete and other non-wood construction types, a primary factor has been which supplier and which species of wood could be the most competitive cost-wise. But also we do consider that each species of wood will be very different in terms of their grain, the amount of knots, the sizes of knots that they have, and because these are softwoods predominantly, they're used for lumber, and so the finish aspect of it hasn't been that much of a consideration, because the lumber use in traditional use of these species of wood has been like you use it for structural frame, but then you cover it up. Now that that's being exposed, I think this is where I think the potential and really where I think the advantages of the hardwoods could come in, because most of the hardwoods are really known for their aesthetic qualities, right? You have the beautiful oaks, the maples, the cherries, and many research is being done in which there's a mixing of a CLT core in which the inner layers, which are not visible, could be done in softwood, but then the visible layers where people would want to appreciate that aesthetic of the different types of hardwoods, you would then laminate or make the outer visible layer on the visible side of the CLT in hardwood. So there's a lot of research going on with the gluing technology, the mix of the species between softwoods and hardwoods, as well as the other yellow poplar or tulip, in which the entire CLT is hardwood. So I think as the industry matures and more of these mass timber buildings are built, there'll be more specificity in terms of the variety of different species and the aesthetic considerations that people would want to have. Because really the advantage of mass timber buildings is that you expose the structure instead of covering it up. So there's less finishes, less materials. All of that then equates to a more sustainable building, less carbon emissions.
And I guess also to follow up on the question of the sourcing of the timber, for example, in the Adobe Hall project, where the supplier ultimately is Austria-based, but the project is in the US. So in terms of logistics and shipping, is that, let's say, carbon footprint, does that become negligible compared to the embodied carbon of the building? Or, like, is it just because it's more cost competitive with that supplier compared to a local supplier?
That's super important, because transportation costs are the same regardless of whether you have wood, steel, or concrete, right? I would qualify that, because a lot of our transportation cost is based on weight, right? And so if you're shipping the same amount of volume in terms of concrete or steel versus wood, the wood is lighter, so it will be less transportation costs. But also, it's not just a matter of distance, but it's a matter of the mode of transportation. So if you were to truck a CLT that was fabricated in, let's say, Oregon to our site in Arkansas, that would actually have a larger carbon footprint than actually shipping it over a cargo ship from Europe by boat, because the carbon footprint of shipping is far less than trucking. So distance isn't the only issue. That being said, CLT production and mass timber production is happening, and I think exponentially these factories are being built year after year. So when we did our Adobe Hall, one of the reasons why we went to a European supplier was that at that time there was no manufacturer of wood in the Southeast United States region. We didn't have a choice. We wanted to use local wood for it. But since our project, given the success of the project, it really proliferated the advancement of using the local southern region trees. And so there's now been 2 CLT plants that have opened up, one in Arkansas, one in Alabama, that uses the southern species of wood in the United States, so that CLT doesn't have to be trucked in or shipped from faraway places, but it's to the region itself. And that's happening where, if you look at the map of the United States as well as map of other countries where they're heavily based forested areas, you will see cross laminated timber and other mass timber plants being opened up right in that area, given the economy of doing so.
Great, thank you so much. Maybe we'll open it to some of the audience questions now, Tom.
Yeah. The first one was from Vicky. Like, he said the wood becomes charred after fire. What's happened after it's become black? Do you remove the char and make the member smaller and continue to use it?
That's a really good question, and I think that's something that I think as a building industry we really haven't thought about so much. So the way it's designed in terms of the code, the charring layer is considered in the structural member sizing. So if your building is rated for an hour then you have to account for like roughly about an inch of charring that happens in an hour of fire, right? For that mass timber member. If it's 2 hours, then it's more like inch and a half, inch and 3/4. And so what happens after that? If there's a catastrophic fire and the structure is damaged, usually the way we've designed our building so far, irrespective of materials, is that if there's a catastrophic fire, that building is designed to withstand, have a structural integrity so that the people inside can escape, can safely get out, right? But what happens usually after a fire is that buildings are demolished, right? So in case of mass timber, where the structural integrity is maintained, you can theoretically get rid of the char, but then then the remaining wood doesn't have, if it was designed for 1 hour, it doesn't have that 1 hour anymore, because once it's chars again, then you're going to have less wood, and so on. So theoretically, can you oversize it so that you can actually scrape off the char and make that happen? Yes. No one's, I don't think, ever have done that, and I'm not aware of buildings where after a fire that unless it's kind of in a localized area where it gets replaced, that the building has been used that way, and I think this is usually the case with most structures. But I think inherently with wood, what's interesting is that it's far more easier to adapt and to renovate than steel or concrete, I would say, so that you could easily take members out and replace it. If there's the other damages, you could easily sand it, fill it with wood, all of these things. So I think this is a topic that we're going to be studying more and more in conjunction with, I think, the other area of catastrophic kind of events in terms of earthquakes and resiliency, and the images that I shared with you about the testing of full-size mock-ups for earthquakes. So if we can design our buildings to be resilient in earthquakes and be salvaged and to be used again, then surely I think with fire, we should have other strategies, right? There's also like intumescent coatings on wood that you can use and apply, so that it kind of creates this foam, so that protects the wood, so that it doesn't have to char. So there's many different ways to, I think, consider that question going forward.
I guess the second question from Vicky, you kind of already answered. Yeah.
The details.
Right. Yeah.
Florence, any other questions?
Yes. This might be a question for you, John, actually.
No, I want to ask him a
Is
question.
the hardwood in US coming from plantation or by selective logging of the natural forest? Are there hardwood plantation in the US?
So I'm not sure about the hardwood, but in terms of the softwood that I've been aware in the buildings that we've done, it all depends on the region of the country. So in the southeast, you'll do primarily, there are tree plantations where they grow southern yellow pine, right? And they manage that in a sustainable way so that you could continue to grow more than you harvest. But if you look at like the northeast, there's no plantations. So the trees that are being harvested for mass timber, it's selectively, and you don't replant, but you selectively harvest so that it allows the forest ground floor and the seedlings that are naturally regenerating to have enough sunlight so that the forest can regenerate itself. And so it depends on which area of the country and which practices historically have been happening. So the answer is both, I would say. Yeah. I see a
No, let Tom finish.
I was going to say, I see a question about bamboo, about how it's prevalent. I would say very, very possible. And the reason I say this is for all of our design building, the species of wood that we use was called black spruce, which grows up in the sort of the northern regions of Canada. And because it's so cold, those trees are really tiny. After 35 years, they're only about 4 inches in diameter. So imagine like how much wood you could get out of that, not very much. So instead of using that for typically like a 2x4 or 2x6 lumber production, what they do, and the company is Nordic out of Canada that uses black spruce, they will make tiny little laminates for CLT, so and glue lamps. So if you look at our over design building and the structure, the laminates, instead of like being 2 by 6, they're like 1.5 inches by 1.5 inches, really small pieces that are block glued together. And so I would think that that similar type of technology can be used with bamboo, which naturally has a smaller cross section and also is hollow in the middle.
Okay.
I can also supplement that in 2 months' time, AIA Hong Kong is going to have a webinar on specifically on bamboo and using it as a structure.
Mhm.
It is something that is still under research stage, but at least there are scientists that are working on it. Sorry, John, in
Okay.
addition to you, I also have other sponsors.
About the hardwood forest, nearly all of the US hardwood forests are naturally renewable. So we harvest it, we do selective cutting, harvest, so so I can give you an example, like when Mr. Al Gore was vice president, and he has, we talked about the softwood, then because softwood was clear cut, most of the softwood is clear cutting, and so if you harvest the softwood in most of the area, it will affect the habitats like the birds and the deers, But for the US hardwood, it won't affect the habitat, only 20, at the most is around 20% of in the area, you harvest the hardwood, selective cutting, when it grows, when the trees are old enough, mature enough, you select, you cut it, and then you let, just like Tom said that, some of the softwood the same, let the, the canopy, you can get this, the area, the young trees and get the nutrients, get the sunlight, and then they grow, and so it won't affect the habitat. So this is one area, the American hardwood and the US hardwood is different than the tropicals, The most of them they select the clear cutting, Okay, and same similar to the softwood in the United States, but in the United States the softwood it takes less year, to the trees to grow mature, so maybe 30 years, from 20 to 40 years, but for the hardwood, close to 80 years, 80. So quite long,
Wow.
Yeah.
I think, John, you also answered Edward's question. And
Yeah, and Tom, I have a question, about this, the mass timber and the cross laminated, for tall building. The building code, is it the same as for most of for all the species in the United States? Like the spruce and the fir, and the pine, and the southern yellow pine. Are there any difference on the building code? And suppose United States building code, can you apply the building code and get the endorsement in China and other places if they want to build in UK? Yeah.
In terms of building code, it's the same regarding species. As long as the species is accepted and can pass the CLT production specifications, then the use of it in terms of building code is all the same. But depending on the species, each species has to be tested and approved to meet in US and North America. It's called a PRG 320 is the specifications for CLT. And as long as that meets that and it's tested and passes that, then it's just like you could use it for irrespective of like of building codes. You can just use it where CLT is allowed and the provisions are made for in the code. So once that material the species is tested, then you don't have to worry about it for the code. It's acceptable wherever CLT is allowed in the building code. Was there a second part of that question I forgot that you asked?
No, I think
the building code in United States, is it the same? You can get endorsement in the other.
So I think the International Building Code is a council that is represented by many jurisdictions, right?
Uh,
But in terms of reciprocity, I think that's, I would say, dependent on each country and each jurisdiction. So what I know, what I've mentioned, was in terms of the proliferation and the expanding of cross-laminated timber use for building heights and building areas. That's been approved by IBC, and it's been adopted. Even in the United States, it happens state by state. So each jurisdiction has to approve it. So
oh,
IBC code-wise, it's been approved, but like some states have adopted it right away. Some states are still waiting. So that's, I think, one of the kind of the aspects of being an architect, is that you have to know the code, but you have to have conversations with people that are in charge of enforcing that code in each building area that you're working in, to make sure you have those conversations and make sure that they're on board as well.
So I have a question here. Thank you, John, thank you, Tom, for sharing. And when you were showing the projects, the structures are beautiful with the wood and the connectors. And there were projects that has only CLT mass timber. And there were the first project that you shared that actually has CLT and steel and also concrete. So what I want to ask is it more challenging when you have more different types of structural materials in the engineering design, or is it actually easier? And and whether there are other considerations you have when you decided on the structural design.
I think it depends. I think the biggest factor is when you consider precision and whether that structural member is made in the factory or made on the site. So working and coordinating between, let's say, those steel transfer beams or cantilever beams and the mass timber CLT and glulam structure, because they're both made in the factory and brought to the site, and we know precisely the dimensions of those elements, it's easy to design and to detail those. Where it becomes most tricky are those elements that are being constructed on site. So especially like site poured concrete. Because of the process, there's inherently a bigger tolerance, right? So concrete, usually the industry standard is that you could get up to like a 1/4 inch tolerance per floor, roughly, right? So for a building that is about 5-6 stories tall for our Arkansas, that's over like 1.5 inches across from the bottom of the structure to the top, and that by code, by industry standard, you're allowed to have that tolerance. So if that concrete wall that they're pouring isn't exactly straight and it's off by like 1.5 inches at the top, that's acceptable. Whereas with mass timber, because these are precisely shaped and cut with CNC machines, the level of tolerance and precision is 1/16 of an inch. So it's absolutely dead precise. So we, on our Adobe Hall project, we had the most amount of time in construction with adjustments between the connection between the mass timber components and the concrete. We had cases where the timber components were absolutely the same size, but the concrete was like leaning towards the timber like 1.5 inches. In another case, it was leaning away from timber 1.5 inches. So we, after kind of looking at that, we had to make details where we could allow for that in-field adjustability. So we had like different mounting brackets and slotted connections that would allow for that to happen. And so the detail that I showed you, where there's a super precise connection between the glulam column and the glulam beam, where you have these pre-installed like slide-on connectors, that we could still do from timber to timber connections. But where the timber had to meet the concrete, we couldn't do that anymore, and we had to come up with a slightly different slotted connector that would work. So a lot of these things you learn from like project to project, and it sort of becomes part of your kind of catalog of details to look out for in the next project that you do.
Wow, impressive. Well, maybe we'll take the last questions. Yeah.
Yeah, sure. There's a question from the audience. Were the two projects, I'm not sure I understand this, deemed to satisfied approved or through performance-based approval? And were there limitations in the percentage of exposed timber areas?
Yeah. So both projects had a lot of differences too. And another difference was about the code and what was allowable. So for the design building at UMass Amherst, that was the first project that we worked on, and that's, we started that in 2012, and construction happened from 2015 to 17. So through the approvals process, actually cross-laminated timber was not part of the heavy timber code in the United States when we were designing that building. It became adopted around 2015. But we were going through code approvals 2013, 2014. So what we had to do was, since there was no prescriptive in the code acknowledgement of CLT as heavy timber, we had to go, and also the fact that we used CLT not just for the gravity loads, but as I showed in the presentation, for lateral loads, for the shear cores. That entire project was a variance request, and it was based under a performance code part of the structural part of the code, where we had to show equal or superior structural performance as compared to what the prescriptive code allowed. And so this is why I mentioned that conversations early on with the local authority having jurisdiction is super important, because we communicated very early, once we knew that we were going to go to the mass timber structure, that this is what the university was planning to do for sustainability benefits, for the reputation of the university, and really have a conversation and really educate the code officials. And so our code official in the Amherst area was super supportive, right on board. And even though we had to go through a variance process, he wrote a letter of support in our variance request, and it passed without really any issues. In contrast, at Arkansas, a different part of the country, different region, different adaptability of code. They weren't as progressive in terms of building code adoption as the northeast of United States tends to be. And so that project we started in the mass timber, and the very first meeting we had, we went through the same presentation, and the code official, the fire marshal in that case, said, I understand what the university is trying to do, but I'll tell you right now, I'm not going to give you any variance, right? So we had to then, and again, thankfully, this was 4 years later when we were doing the design, and by then CLT was approved and prescriptively accepted into code, and all of those charring calculations under type 4 category is already there prescriptively. So we went through an Arkansas project without any variance. Every single piece of that timber that's used is prescriptively done and not performance-based. So it's possible to do either approach. It all depends on the extent of mass timber and for what structural purposes you're using. And it also depends on size of the building and the height of the building. We were under the, I think the 85 feet height for being able to expose all of the timber. So we were able to expose essentially where we wanted to cover it up because of the mechanical ducts and things like that. That was by choice. But otherwise, we exposed essentially all of the mass timber structure that we wanted to expose, and there was no limitation. But if you look at the current code in the United States, there's categories. I think first is up to 8 stories, in which case you can expose all of the mass timber, and then up to 12 stories, I think you can expose up to, I think it's 30%. And then if you go 18 stories, then you have to, I think, cover most of it up. But now, again, with the second variation of code, that's also changing with additional fire tests so that more and more mass timber could be exposed.
Well, Tom, thank you so much for today's presentation. I can feel for your passion about mass timber.
Yes.
And you really convinced at least me that there is so much benefit out of mass timber. So thank you again. And I should also thank John for introducing you to us. Yeah. So thank you, John.
We're so happy that we get together again, in 3 years, and in the future, we invite you to come, okay, to China, to Southeast Asia.
I'll take up on that offer.
Okay.
Thank you for inviting me. It's been my pleasure, and so I hope you guys have a nice, relaxing evening. I'm off to my work as my workday just begins here. So
Yeah, before we end the webinar, I also want to give everyone a heads up. As I said before, this is the first of the 3-part series.
Yeah.
The second one is going to be, again, AIA, but this time Shanghai chapters are going to host this on a topic called Fighting the Climate, Biophilic Environmental Design with Wood. This is going to be January 9th. So it's only 1 week.
2 weeks.
2 weeks from now. Yeah.
June 9th.
June 9th. Yeah.
June 9th.
June 9th. Yeah. So that's coming up.
Yeah.
And then yet another one that is going to come up as well is from our AIA international chapter from Taiwan,
Yeah, right.
like in Taipei. This one is coming on the June 25th, which is also focusing on how wood as a sustainable materials are going to be applied in architecture and interiors.
Yeah.
Okay, so stay tuned. I mean, these notice will be coming in from Shanghai, from international, but the Hong Kong chapter will make sure that you get circulated. So thank you again for joining us. And thank you, Tom. Have a good day or good evening, everyone. Bye-bye.
bye. Thank you.
Bye-bye, Tom.
Bye-bye.
Bye-bye.